Dan Miracle and Ray Coloni, who talked about essentially use of creation of technical specs, use of technical specs, discovering technical specs, and things of that kind. I mean, if you want to abstract their talk. And then Amit Sheikh mentioned the semantic web vision and how it can be used in a number of applications. So what I'll try to do is to bridge the two and try to show you how semantics can be used in the context of materials. So I have two primary goals. So one is to give you some simple examples involving materials and process specs, and convey to you using very simple examples what semantics will do for us, and then sort of sketch a continuum of use of semantics, starting from lightweight semantics to more detailed one, where the initial steps is more engineering because we know how to do it, and then there are other issues that are still open-ended and require a lot of research. So you'll see a general space of things that we can do in the short term and in the long term. So in the outline, I will just quickly recap the domain goals and challenges which will drive our further steps, and briefly mention the cyber infrastructure investments that are in science to give you a sense of what else has happened in other communities, and then look at the utility and continuum of machine processable semantics that we advocate. And here I'll just quickly mention different sorts of data and the granularity of semantics, and say a few words about the benefits of lightweight semantics, and then how we achieve that and provide larger architecture that we are aiming for. And then if I have time, I'll also mention briefly some research aspects in processing tabular data. Now, some of the examples that I have in these overheads are from my experience a decade back in the context of using materials and process specs in the legacy, say, aerospace materials kind of domain. So the basic idea is to enable domain scientists to both share and discover data. And for that, we want domain scientists to be able to do that and be willing to do it. So essentially that translates to two sets of challenges. So we have technological challenges to build tools and repositories that are easy to use for the domain scientists to share data. And we also have cultural challenges in the sense that we want to provide control on the data that they have created. So that leads us to the idea of keeping track of the provenance and also keeping track of the access control and things of that sort, so that you can selectively share or keep the data private and be of broader interest in practice. Now, if you consider the kinds of cyber infrastructure work that has gone to pass, you can broadly cut it into two parts. So some things that we call as working towards short tail of science data, and orthogonal to that is the long tail of science data. So in the first category, you have large amounts of data, but they are relatively more homogeneous, and you can potentially have more formal approaches trying to support search and discovery and analytics and things like that. And for this, you can build data centers and grids, but that does require very experienced IT specialists to work on. So in contrast, we are also interested in looking at smaller sets of data, but then these span multiple domains, multiple vocabularies, and things like that, and also include legacy data. Now here, we want to make it easy for people to share data on the will allow us to basically share material science, engineering data and documents. And this will be the foundation for data discovery, integration, interoperability, and things of those kinds of activities. So let's briefly look at the nature of technical data that we process in the materials context. So predominantly the documents are heterogeneous in nature, and the heterogeneity comes from both syntactic heterogeneity and semantic heterogeneity. So the documents can be publications or technical specs that contain text information, numerical information. They differ based on units of measure, vocabulary used. They may even contain images and equations and things like that. So it's a very diverse data, and then there's a lot of interesting data captured in tabular form. But these tables are not regular rectangular structures, but they are actually highly irregular and heterogeneous. So they are quite hard to process mechanisms. So here is a very simple fragment from legacy materials and process spec. This spec was created probably in the late 50s and was revised in the 90s and things like that. Now when we look at that, it's relatively easier to figure out exactly what it is trying to say. On the other hand, if I were to make that machine processable, I need to sort of first discover from the entire text of the spec that this is regarding titanium alloy that has 4 types, bars, wires, forgings, and rings. And then this describes composition, and then in order to specify exactly what this table is saying, I need to understand exactly what the 2 dashes mean, what the word residual elements signify. And then if you look carefully at the subsections, we see that there are additional stipulations such as hydrogen content of forgings may be as high as some number. So you need to understand that this entire spec is applicable for 4 types of data, and then there are additional or exceptional stipulations for a particular form and things of that sort. So the main thing is to notice that what is evident to us needs to be made explicit when we want to make this machine processable. So we need the background knowledge to figure out exactly what many of these words actually imply in terms of the percentage content and things of that sort. So let me give you some very simple examples of what does semantics actually provide. So it allows us to basically understand what is explicitly written in a document. So what we write and what we really mean. So to begin with some very simple examples, so things like chemistry, chemical composition, chemical analysis. So these 3 are equivalent. And so we should be able to create a simple dictionary that captures that. And of course the similarity is evident by looking at just the strings. That's probably the easiest of the cases. But then you may consider a significant difference between, let's say, chemistry of ingot versus chemistry of product. So maybe that distinction is important, and you may need to make that explicit. Similarly, you look at strings such as delivery condition, surface finish as required by purchaser. Now they may have the same intent, but that's not easy to glean by essentially string analysis. So you need to create extra thesaurus to capture this kind of a background knowledge. Now when we consider, let's say, processing a text of materials and process spec, you may have a heading which says welded tubing. And then in the concrete description, you may have words like tubing, which actually is considered a superclass of welded tubing, but in the actual context of use, tubing refers to the welded tubing. And so we need to make that connection and go on. So, and then if you look at more detailed spec, a process is basically specified using a collection So given a sentence, you need to figure out exactly what piece of text corresponds to a parameter or characteristic, normalize that, understand what it means, what the corresponding value is based on where it appears in the text, and then summarize that in a formal sense that we can machine process. So there are many times where the occurrence of control term needs to be reverse engineered and we need to figure out exactly what kind of parameter does that refer to. Now that requires background knowledge. So something that comes naturally to a domain scientist needs to be made explicit in the background for us to be able to meaningfully process these textual specifications. So the semantics, the goal of semantics empowered analysis and semantic web technology is to make this possible. Now the way we plan to go about is to consider a continuum in this context. So we'll begin with lightweight semantics where you can associate with files and documents some metadata that captures the content that it corresponds to and also some provenance information that specifies exactly who created it or where did it appear and things like that. So that also is required for us to say how reliable some work is and make our own assumption about what to use and what not to use. And then we can progressively make that richer by going into the text of the document and annotate. And I'll give you some concrete examples of that. And then the annotations and the background knowledge, the rich domain knowledge, will allow us to come up with powerful search techniques which are closer to how a domain scientist thinks as opposed to what is explicitly written in a concrete document. And that's the thing that we really want the machines to do so that the work of domain scientists is reduced. And in some sense, these are mechanical things that we can try to offload from us. And eventually, we can turn these into fine-grained data nuggets with annotations in order to do reasoning and combine specs, compare specs, and things of those kinds. So those are much harder to do, but again, I'll give you some examples to show you what have been attempted. So here is something that we did about a decade or so back, and so what I'm showing you is a real legacy spec corresponding to this titanium alloy. It's actually an aerospace material spec 48299. So essentially at the process level, let's say you just identify what are the processes that are being discussed in this spec, and maybe delimit those paragraphs that talk about that process. So on the right hand side, we have the list of processes that this specification is specifying. So you have chemical composition, you have melt methods, specifies delivery condition, has some treatment, has tensile properties described, and has microstructure exam and things like that. So the courses level specification summary may be just capturing what kind of information is included in the spec. And then we can go, so this is what I call the lightweight semantics. Now we can go the next step and go into the text of the document further and then go parse out phrases and then map them to the concepts in the domain. So for example, so in here we are describing, let's say, a melt method, and there are two kinds of melt methods. So melt method primary and final, and then there are other details about how this particular method is performed. Now once you have these annotated documents, you can potentially turn that into a concrete spec that can be machine manipulated. So for example, here is a syntax of the translation modeled after, let's say, a programming language. So this particular specification is something that we can programmatically But at the same time, you try to make sure that it is also readable so that you can connect the translation to the original, because for traceability reasons, that connection is important. So the bottom line is that in the long run, one could potentially summarize specs in a formal way, and then you can use semantic web technologies that are coming up now that we did not have access to at that point, to actually make this into some document that we can put on the linked open data and manipulate. So for example, if you are searching for work by somebody else about characterizing a particular material, you could issue appropriate queries and fetch all the relevant information, aggregate the data for local analysis. So with that sort of some example in the domain, let me just kind of step back and say that what we want to do is to proceed by starting from something really simple that we know how to do right now, which is to begin with lightweight semantics. So we want to use lightweight semantics so as to basically have it easy to use by the domain scientists and can be more widely applicable. And then as we proceed further, we could go deeper into the actual document and further refine and do fine-grained approach. And we also believe that this entire process will preserve the existing investment. So if your need is to do basically search and discovery of documents and files, then the lightweight semantics is probably the right thing to do. On the other hand, if you want to compare specs, combine specs, or analyze specs, then you need to invest the extra effort and then you get the payoff. So there is a continuum and cost-benefit trade-off that we need to work through in order to understand and use these things. So let me skip over this. So now, so how do we go about starting up and building these kinds of infrastructures? So our idea is to first begin with some kind of a community agreed upon controlled vocabularies or ontologies and things of that sort. So take whatever the domain ontologies that have been developed for different segments of the materials landscape, and then try to put them together, and then use that to tag your documents and data as a first step. And then as we proceed further, we could do that more fine-grained. So in the infrastructure, we could begin by registering data, associating metadata with these documents, and have a simple search mechanism to access whatever is out there. And then we also will understand the need and the role of both provenance and providing access control mechanism for practical use. So that's other thing that we plan to work on as we proceed. And we also think that to promote data sharing, it is important for us to keep track of provenance and also give credit for whatever is shared to have a broader acceptance. And many of these kinds of things can be done using semantic web technologies as it's being developed. Let me skip over these details, but let me just mention the following. So if you consider the broader domain, there are two sorts of issues. So one is where you have commonly accepted vocabularies, in which case we can use them, or there may be cases where there are different communities where the vocabularies are very well entrenched in each of these communities, in which case we need to consider federated services. So we need some way of mediating between these entities, so that given a query that the user issues, we need to translate that into the forms that are meaningful to each of these components of the federation, and sort of mediate between them. So those are the two approaches that we need to take in order to deal with more practical scenarios. So I have And so the goal there is to have machines help keeping things updated on their web page. And to enable that, we have the use of linked open data, and in this particular case it is powered by Wikipedia and music brains in the context of entertainment domain. The linked data open data essentially revolves around creating information about entities and providing that in a concrete, searchable, navigable, reasonable, convenient for reasoning form by thinking of the entire information in terms of basically relationships and instances of relationships. So here is a small fragment of information regarding John F. Kennedy. Now this linked data can be created by different people, and then you can connect them based on the related pieces and eventually promote aggregation of information automatically. Here is the state of linked open data created, I think about a year, I think in 2011, that has about 300 ovals, and each of them has millions and millions of triples. So let me just speed up a bit and show you the overall architecture we are envisioning for the material science infrastructure. So at one end of the spectrum, we have this heterogeneous data that we can upload and explicitly provide the metadata to begin with. And then that data will be stored in this metadata store registry and is immediately searchable on the metadata that you have created. Now, as we proceed, we can extract, we can annotate the data and extract information from inside the document and then provide richer search functionality. And then if you have different ontologies that allow you to mediate between different vocabularies, then that can support semantic search. And faceted search refers to searching for information based not only on the content but also on the provenance issues such as who is the author or which organizations are supporting a document, things of that sort. And then eventually the part in the dotted line essentially refers to creating fine-grained translations of these technical specifications that can be reasoned with, combined, compared, and things of that sort, which is the long-term goal that we have. I had some more slides on processing tabular data that actually requires non-trivial work. So I'm just going to throw at you a concrete example. So here is a real specification of tensile property. And again, to really turn this into a mechanically processable, machine processable data requires a lot of work. Because what is contained are information about a lot of different parameters, and many of the values are conditioned on, let's say, the shape of the specimen, the size of the specimen, and things like that. So we need to capture that properly before we can meaningfully use these numbers. And then furthermore, many of these tables have a bunch of nodes that actually modify these entries in non-trivial ways. So in order to understand the space of all the combinations that this is trying to capture and do that in a rigorous manner is a non-trivial task and is not definitely doable automatically from scratch. So we do have some ideas about how to eventually go about doing that. So we understand that this is meant for human consumption and these are very complex, and so one viable technique would be to come up with well-defined regular structures that have well-defined meanings that we can automatically use to translate to this linked open data kind of format. And then the task of going from this actual complex table into these regular forms should be left to human beings. So the humans provide semantic disambiguation and first level translation that does require some intellectual work, and then have the mechanical task of converting that into the lower level form best left to machine. So that's the kind of thing that we have in the long and so that completes my talk. And so basically the two things that I want to try to get across is some of these concrete examples where semantic technology and the background knowledge we can create will help in reducing the labor that a domain scientist will put in processing some of these things, and will have better access to the documents and data that are around. And the second thing is to provide you with some idea of the continuum where we can start from things that we understand well and then systematically refine them to get more detailed reasoning and applications. And as we improve matters, we pay the price in terms of the effort required and what we can get.
T.K., you talked about the complexity and the difficulty in taking in tabular data and then making that machine processable. And so that's the difficulty with trying to bring in legacy information that might be stored in different locations. But if you were to start from scratch and develop an ontology that represents that table and use that from this point forward, then it's trivial to get the information linked up to that ontology. Is that correct?
Yeah, actually, in some sense you clarified it nicely. So basically what I'm saying is that we could start with well-defined tables, convert that into the lower level forms automatically, and we can use those well-defined forms to take the legacy tables and put them into this form. But the task of taking legacy tables and putting them into these regular forms is left to us, and that cannot be done mechanically. Yeah.
Have you looked at graphic data, XY charts and data diagrams, for example? I mean, is there a similar approach to sort of mapping the structure of those and then determining the semantic relationships?
Actually, what we have actually tried to do is to take these documents and programmatically isolate tables and then see if we can convert that into some other forms. And as long as the tables are relatively regular, we have been able to successfully do that. And we can design a translation algorithm. For example, if the tables are about composition, then there are many that are easier to handle. But the one that I showed you about tensile properties, those are very hard to handle. So we have, again, there is a continuum. I mean, there are things that are relatively more regular that are easy to process, and there are really difficult ones.
So basically, we have two very different level of annotations. One is to annotate every element within an object. Object in this case is a table, but object can be a video, image, a diagram, whatever you want. In some of those cases, which are simply a pixel or image, there isn't much to automatically do. You can't, But what you can do there, and that is quite useful, is that you can still process all the captions. You can potentially process the text surrounding that. So when I showed you that a system we built for audio video search on the web, you crawl the website and look for any audio or video, and then audio video itself within the audio video is not indexed. But all the caption, all the text around that is possibly indexed. It can be indexed. So sometimes in audio video we can even look at the metadata embedded within the thing and also pull that off. Like MPEG 4, you can pull off the metadata from there. So again, it's that kind of thing. So typically, pixelized data is not something we would do anything automatically. Human has to interpret it. But non-pixelized data, whether the metadata embedded in the digital file itself or anything surrounding in a textual form, we can potentially automatically annotate, which is good enough. In most cases, say this table. Tell me about all the tables which are about this concept, and that is in the caption. Well, we can get you that now. You will get, you will have solved 90% of problem. You have to do the 10%.
Yeah, actually, materials context, like you mentioned. I mean, if you are looking at, let's say, microstructure images and things of that kind, so we can index the caption and then use that to access those photos, and then of course we'll have humans kind of look at it.
The important thing is that that caption would be indexed with regards to your ontology, that's common term. So your source term would map very well with the kind of whatever text they have used, because the transformation has been done when you did the annotation.
And there are, potentially you could then link to a technology that could look at that image, measure the grain sizes, and
right. That is, if you have sort of the photo processing thing that can sort of say extract that kind of information and parameterize in text form, then we are back to our old approaches of using that in the user. Thank you.
Thank you. Now I'm just going to say a few words about federated architectures, provenance, and access.
All right, we're going to now move on to the architecture. How do you construct a system that we can use built upon the fundamentals of semantic web that we already discussed so far? So this is about the federated architecture, provenance and access control. There are a lot of practical issues about data being proprietary and things of that nature. So I'm going to address outline solutions that we have, or that we can have, to deal with that very important issue. Just to kind of give background, these are the two projects that we are currently carrying out, and there are 4 faculty level people. There are a number of students who are working on this, and so this kind of collective work from this team. So this is a step of the kind of 7 step process from discovery to deployment that appears in this document. I think should be that should be rather familiar with many of you. Data at all steps of the process, and you want to be able to access the data at all these levels, created any time during this whole process. So the idea is that during this whole process, your data will be in lab notes, your data will be in personal desktops, your data will be in databases. Now, lab notes, as in not digital form, would be of course hard to access unless you have a metadata about what is in those notes. But anything that is digital is something that we want to give kind of a single point access to at people at different level. So you have to kind of think about public-private data sharing framework. In particular, you have certain data that is private. This ongoing experimental data, certain data that you say this is your intellectual property, not to be shared. There will be selectively shared data. For example, you want to share data with collaborators or license it under certain circumstances. And there will be public data, your release products, material specifications, something you had to give it to the government if you are a contractor and government contracts call for you to be made public, or just otherwise you want to make it public because you want others to find it. And or other government produced data that may be public, academic data that may be public also. So to be able to deal with the data of all variety of this kind, you can really think of this federated architecture. And the, in fact, let me see in the next, I'll come back to slide. But the principle of federation means that each component controls access to its own local data independently. They have local autonomy. They have right to say this is my private data and not be made accessible, or they have right to say what part of the data should be made public or shared in a limited form. And that there will be some techniques whereby a query can be posed against all the data out there, public, private, shared, but subject to the rights and access control that will manage the level of sharing. The query will be processed. So it may not really give you answer to something that is confidential or private. And the results are coming from variety of sources can be combined together to give the user integrated access to the data that for the query that user has posed. So variety of things that happen here is that you have data and you have different organizations, and each of them have data that are public, shared, private. You have access control processor, you have query processor, and you have federated access layer. So you have users, they are authenticated. You have federated semantic query processors, so that can take your query and process against multiple sources. You have mappings, saying there is some data here that is the same as some data here, and the system gives you integrated results rather than giving you bits and pieces that are for you to collect together. So so that is broadly, and I mean I right now want to just introduce the concepts. There is a lot more detail that we can go into the things. In fact, it goes back to the 1980s when I worked on 3 large federated database projects. The other very important concept here is provenance. So provenance is something that explains the origin of an artifact, any object that you have, any data that you collected. It says how was it created, who created it, when was it created, under what condition it was created. For example, in the mass spectroscopy example I gave earlier, all the machine settings that were used under which the data was created became part of the metadata that was part of the provenance of that data. Because you want, so suppose I did 2 different experiments, both produced data, but there were different settings that were created, or different testing that and then the data won't be comparable unless I'm able to factor in under what conditions those data were created. I can bring both the data to be together, and I will have larger data to evaluate if the data were compatible in some form. But how would you know they're compatible? For that you need the provenance information. For a given material, which processes and properties were involved, input and output values of those processes, and perform this. You remember in the one of the slides I showed, I had object properties. So that starts to kind of collect the data of that kind, or metadata of that kind, and that is then queryable. So not just the data that is created, but all the provenance, like the conditions under which data is created, is all queryable, all accessible. And the provenance gives you verification, reproducibility, trust, testing, quality, ranking, what is more important based on who created what, when it was created, using what machine and process it was created. All these things can be done. Because data, if you can't trust the data, it is of no it's not valid. Right? So it should be an integral part of any system that you do. So Claire had shared this particular diagram. You have some input, there is a process, some output, and capturing the provenance to give you sufficient accurate information to reproduce the same output. For example, you want to recreate an experiment, well, you look at the provenance information and recreate it, things of that nature. But all the variety of parameters, properties that are there at all stages of the process will be captured and logged in the provenance model. Now there exists some preliminary, some very useful and readily usable work called pro-ontology. The Worldwide Consortium. Remember I showed you the standards. I didn't show you all of them. One of the latest one is this pro-ontology, which is a worldwide standard for modeling provenance of data, workflow, and things of that nature. So what we are proposing and planning to do is to capture data in the Pro, which is generic model for provenance modeling with domain-specific provenance. What is relevant to the material science itself. So again, going back to mass spectroscopy example, what cell line did you use as an input? Now the cell line is very unique to that particular biological data processing. So that has to be also, that is modeled in a domain ontology, domain model, along with all the generic things like who produced it and what program was used, which is generic. So you need both domain independent and domain specific aspects in your domain, in your provenance, and we plan to model all. This will be represented standard RDF, and you have query engine that will support provenance or the queries. There are operators that are explicitly made for comparing artifacts of provenance. Now, okay, so let's talk a little bit about the sharing part of it. So, a semantic web data, going a little bit in the details. So here you have a triple. So RDF is basically a triple, and you have a subject. Eric Miller here is a predicate doctor. His title is doctor. So title of Eric Miller is doctor. That kind of thing is what is captured. And this is linked data. TK already talked about linked data to some extent, and what we propose to do is to provide an infrastructure whereby the linked data would have both public and shared data. So you can associate license information on that data, and that it can be accessed only through the query processor that will check that you have the license to use the data as an example. The idea here would be that what happens is that G does some processing of the data and chooses to make something shared or public. Pat and Whitley does that, and so on and so forth. And collectively, it may be simply saying, I know how to do this, I will tell you exactly what the results are. Right? So it depends on what you want to make public. But whatever you want to make public, let us have a community-wide way for standard representation and sharing of that. This is becoming that. So there's a lot of data here, for example, in biological and biomedical community that is out there. And they have been able to, they are successfully now finding this as a mechanism to successfully share the data. I think that we can do the same for material science and this particular community. With the addition and better support for the access control part of it, with better support for provenance, with perhaps better management of quality, so the things are more usable. So you can have then in terms of access control, you have individual resources, you have individual triples, and you have entire data set. So the granularity at which you want to support sharing can be at different levels. You can go down to very granular level to much larger level. And you want to be able to have flexibility in selecting any data pieces to be shared at any time. And then how can we choose any part of our data to share in public community or in selected collaborators? So you would have ability for those who are owning the data on top right corner to be able to give out access control. Maybe there are multiple levels. The next slide will show that. There are multiple ways you can do that. And the point here is that so you will be able to creating the resources, you will be granting the permission, and you are going to have infer the permissions. And for example, you give permission to group, you are a member of the group, automatically you have access to that. Those things will be, and the query rewriting will be done to have access control and embedded query execution. There are various policies to be able to do that, role-based access control, mandatory access control, and so on and so forth here. And which policy to support, again depends on organization's need. We think that we have research work and initial prototyping, and we believe that any of these access control mechanism can be extended to support these policies. Or the access control mechanism we have can be used to support all these policies. So the summary here is that we plan to develop semantic federated architecture, and we started to kind of work along that line that will enable us to enhance the open data access, protect confidential information, improve communication between collaborating teams, support reproducibility of material products with confidence and trust, and utilize the power of semantic web standards and technology to do so more easily, effectively, and flexibly. Questions? I of course did cover this at a rather high level, so there is a lot more to it, but essentially it is very important, and Claire certainly wanted to kind of get this out on the table so that this can be then discussed further in our discussions. But clearly, data ownership and these things will be important aspects because industry and private companies are involved here. Yes.
Do you think keeping provenance at the individual statement level, I saw on your one slide, you said triple is realistic to keep basically a full set of auditing and history and all of your provenance statements at that level, you could get a 5 to 10 time explosion of your data. Is it reasonable to really do that security at that level?
So the most important, for me, the more important question is it needed? If it's needed, then yes, it is doable. And the reason it is doable and the conditions in which it is doable is an assumption under which it is doable is that all that the provenance information is created automatically as part of the routine process.
Yeah, so, I understand it's doable. My question is it practical?
Practical in the sense of computational performance or in like storage and speed and all that?
Performance, maintainability, does it?
Yes.
Yes. Is it practical?
Yes, it is. Our ability to create and manage data, is grown substantially now. Our own center has just sent out yesterday a purchase order. We will have 800 and some cores, 17 terabyte main memory, and 250 terabyte disk space just for us. So and this will then support both Hadoop kind of processing or to the parallel processing kind of stuff. So these kind of things are done at scale. I can show you, maybe at the end of the day today or tomorrow, some large scalable systems that we have that can manage this kind of stuff. So these things are, with the cloud computing and variety of other technologies, big data sort of things are really becoming.
So you have a big data triple store for keeping all that?
Yeah, we can create fairly large stores of triples now. And there are cluster ways, and we will step in the discussions to give you more details if you want to get there. But there are clusters, ways implementation of those things available also. And very often, I'll give you an example of a system, and it's a live system that is being commercialized right now. That system analyzes massive amount of, or large amount of, I would say, Twitter data feed right now. For example, we had in first week of Hurricane Sandy 5 million tweets. And the computation of that is pretty heavy, pretty involved, text processing of this kind of data. And the pipeline of processing involves use of future storm for ingesting, and putting all data from multiple sources in NoSQL to triple store to something else, when you're rendering and processing for the visualization. So those architecture implementation levels can be also constructed to deal with storage, performance, computational aspects and such.
I would argue that high quality, high fidelity provenance information is well worth paying for, right? Because you come to find out that this technician never ran that test right, 5 years ago, and you want to get all that information out of your database, or you're trying to discover information, and if you can't figure out who ran the test and where it was run and stuff like that, you might use it for a bar napkin or something like that just to rough something in, but you're not going to be able to use that information to substitute for a test you might have to run of your own. So,
yeah, absolutely.
I mean, I would be, I think that
there are
would
many
be
cases
well
people
worth
have
it
to
if
go
you
back.
want to get into the real deep value of the information that's hiding out there.
I think so. So far, more or less, data reusability is a non-starter if you don't have provenance. You can have the data, but if you can't trust the data, you don't know the quality of data, I don't think that they will be particularly used. People will find results to not trust the data and then consistently make data. So we'll just have to do it. Now the question here is at what granularity you want to do it, and you choose to do it at high level granularity and later you find out that you need it at lower level granularity, then you are, there's a tough luck. Or you will have partial information and things of that nature. But what I can say here is that technologically we can do it. There are a number of other practical questions you want to answer, such as the question that the first question we included. I could have 2 to 10 times more data if once I have provenance and access control added. Right? So yes, indeed we are going to do that. But the point here is, in many cases, if I have one order of magnitude higher number of data, I can handle it. So so far as that will make the data useful in serve the purpose, yes. That's right.
Regarding granularity of access control, what you pictured there was a data set could be protected, a triple could be protected, or a resource could be protected. And by resource, you meant either any part of that triple, the subject, the predicate, or the object.
Yes, you can do any of the level. So, Vin works on. Vin, you want to say something?
In this work, we have different level of granularity, right? So, let's say for the data set, we have leg graph for that. Leg graph is a set of triples, and the triples can be broken down into like a subject, predicate, object. So, our access control approach support all of 3 levels. So by using like a unified framework, so I can show you like the work if you want.
I know that, or I've read that Oracle's triple store has access control down to the triple level. How mature is access control to the resource level?
So they claim that they also support the resource level. That work is done by Matt Perry, one of Dr. Shep's students.
Well, we don't have the commercial grade technology at that level because we're doing this work as we go along right now, and we understand that. But Noesis and I have done companies and products. So if but there are questions whether there's a market, and it can be done. It can be done as a robust prototype, or as a part of a research project, or it can be done if there's real funding behind, or it can be licensed or transferred over or made open source, and others will implement it.
So right now, commercially, it's available. Access control is available to the triple level, but more research is required, and there are no really commercial products that are available at the resource level at this time.
Yes. We are doing the work at the resource level, and we have witnessed the work in that area. But yes, you're right. That's part of understanding whether that is needed, when it is needed, is part of what we are working on.
When you talk about resource, if you're talking about what is identified as a subject or an object of the triple, that resource is identified as its own URI.
Yeah.
And so that URI could be secured in the same way any web page would be secured. So security at that level is not really security whether they can see the object as part of the triple, but more security of once you have identified that there is a resource at the end of one of those URIs, then when you would actually try to hit that resource, it would be secured. So you can have security of an access control over a resource, but securing the triple, the statement, the metadata about that resource is actually a different mechanism.
Yeah, so you don't want to reveal the value, say predicate, you don't want to reveal the value, then you secure that.
So if you secure the access to one resource, right, and one resource is connected to multiple other documents. So we say that for one at triple level, if you want to access the full triple, like one document and its metadata, then you need to have the access to both resource and the properties and the objects. So that is how we can secure the access to the one triple. And the another approach that we are extending our work is like we can represent the triples as a resource. And the way to do that in Semantic Web is to use replication. And we are proposing another approach which is more efficient than standard replication to represent the triple. So there are two other approaches for doing that.
Reification is basically just metadata about that particular triple.
Yes, and you say that one resource is a statement, and that resource is the subject, predicate, and object. So because of that, the size of that is low, and our approach is to say that we can represent the triples by using one instance of the property of that. So by that, like the size of the data set will decrease for the metadata.
All right. Should I go on to the next one, or you're break?
Well, I think we were scheduled to break for lunch at about 11:30.
Okay.
I'd recommend we continue to do that and then just reconvene at the same time, and we'll figure out between now and then exactly what to present in the early afternoon prior to the breakout session.
I think